Hi guys, hello everyone. Uh, in previous video we have seen carbocations, carbanions, those are reaction intermediates. Now we are going to see here free radicals. Okay, in free radicals there are two possible structures we can say here. Two possible structures. Free radical may be a planar species. Okay, you can see here it's a planar species. We can say there are two possible structures. The first one here, the carbon atom bearing odd electron. Okay, the carbon atom bearing odd electron in sp2 hybridized, and odd electron remains present in p orbital. Okay, p orbital shape. It is a shallow pyramid. It looks like a shallow pyramid, we can say here. Okay, this is first type structure. Second structure is the second structure. It looks like neither planar nor tetrahedral, and the orbital containing unpaired electron is some sort of hybrid between pure p orbital and sp3 orbital. Okay, here p orbital is pure orbital, sp3 is hybridized, the hybrid between p and sp3. Okay, you can see here these two types of free radicals are possible. Two possible structures, two types, not possible structures are possible. Free radical is remains same, but different structures. I'll show you here examples. A type how it looks like and B type how it looks like. A type of free radical, it looks like this, you can see here, and B type of free radical, it looks, you can see. All right, this is you see sp2 hybridized. Okay, both are planar only, but it's you can see B is it is in between P and sp3. It looks like that, maybe planar, that's why it is neither planar nor tetrahedral, you can see here. Okay, yeah, it is a shallow pyramid. A type is a shallow pyramid. It's neither a planar nor tetrahedral, we can say here. The hybrid between P and sp3. Okay, B type is. Now, whether free radical exists in planar configuration, okay, in these two forms. Okay, you can see here. The main point is whether it is exists in planar configuration. Okay, let us see that. When you observe, two pyramidal forms are there, already we have seen here. What are those in B? In B here, how many pyramidal forms? Two pyramidal forms. Two pyramidal forms, we can say here. The rapid equilibrium takes place. Rapid equilibrium means constant conversion one form to another form. Rapid equilibrium takes place, we can say here. Okay, yeah. See, it indicates that what it indicates, unpaired electron is in p orbital. Resonance stabilized free radicals are sustainably exist in planar configuration. Yes, which one exists in planar configuration? It is very important point. Keep that in mind. Resonance stabilized free radicals. Resonance stabilized free radicals certainly exist in planar configuration. It is the point we have to keep in mind. Okay, planar configuration, we can say here. Yes, how the free radical is generated? How can the free radical can be generated? We can see here. Free radicals are often produced when a molecule is supplied with sufficient energy. That is thermal or photochemical. Yeah. How the free radical is generated? The first one is by thermal. Or we can say second type is what here? Photochemical. Generation of free radical, we can say here. Generation of free radical. Yes, it can be thermal or photochemical. It can be thermal or photochemical. We can say that. Okay, that is the point we can see here. Mostly homolytic cleavage takes place. Okay, homolysis. These two are formed by homolysis of covalent bond. How they can form? By the homolysis of covalent bond. You keep that in mind. Okay. Now, yeah, in oxidation reduction reactions involving gaining or losing of electron takes place. You can say here oxidation redox reactions. We can say here most probably the loss of single electron or gaining of single electron takes place. It can generate free radicals. Okay. Right, free radicals, some examples. Let us see here. Let us see some examples how the free radical can be generated. Let's see. CH4, sorry, CH3 taken 4 times Pb. It gives rise to, upon heating, the symbol of heating, it gives 4 CH3 plus Pb. Next, CH3 N double bond N. This is diazomethane. Dimethyl diazomethane, we can say here. CH3N2, we can say here. Diazomethane, you can say that. 2CH3 free radicals and removal of N2 gas takes place, we can say here. And next one, what we can say here, C6H5CO OCO C6H5. Yes, this is, yeah, here it is peroxybenzoate. In this case also free radical generation takes place, we can say here. Yeah, let us see that. OCO. Yes, you see here also the generation of peroxy bond is there. You can say that 2C6H5COO free radicals. 2 free radicals will be generated. Now from this what it gives, 2C6H5 free radical plus 2CO2 gas molecules will be generated. You can say here. Next one, CH3 COCH3. It upon by exposing to sunlight, H nu contains UV rays. That's why sunlight contains UV rays. UV rays are responsible for the homolytic. That's why thermal, it is called thermal, photochemical it is, we can say here. CH3 COCH3. The free radicals will be generated in this manner. Now this finally what happens, it finally gives CH3 free radical plus CO. Okay, yeah, carbon monoxide will be removed, we can say here, or C double bond O minus, you can see here. It gives rise to, at anode, what it gives, removal of electron takes place. Anode, electron removal takes place, you can see here, or C double bond O. Okay, O here free radical, you can see here, and R free radical plus CO2, you can say that. Yes, here free radicals are stabilized by what? What are the factors? Okay, yes, free radicals are stabilized by, how they can exist as stable? Stabilized by the following factors. What are those? Here first one, hyperconjugation. You can see here hyperconjugation, and the second one is resonance, and the third, yeah, these two main factors we can say here. Okay, right. These are stabilized by mainly by hyperconjugation and resonance. Okay, you can see here, and you can see that yeah, based on this, primary, secondary, tertiary. If you see here, tertiary butyl, methyl, ethyl. When you observe examples, you can see here. For example, let us take here CH3 free radical and CH3 CH2 free radical. Which is more stable? It is more stable because hyperconjugation, through hyperconjugation it is stabilized. Here hyperconjugated structures are 0, here hyperconjugated structures are 4. As the number of hyperconjugated structures increases, stability increases, you can see here. And the next one, you can see CH3 twice CH, you can see here. It is also a free radical. It gives total how many free radicals? 7 free radicals. Here 0 free radical, 0 hyperconjugated structures. Here 4 hyperconjugated structures. Here total 7 hyperconjugated structures you can observe. Now when you take here CH3 thrice, you can go through my hyperconjugation structure video. I have explained what is actually hyperconjugation in previous videos. You can go through there. Right, now here how many total hyperconjugated structures? 10. Okay, yes, right. Here when you observe here, for example, allyl free radicals, allyl and benzyl free radicals, we can see here because of resonance. See this example for first one, hyperconjugation, and this example, and the second one for resonance, how can they stabilize? We can see here in the next page. You can see second case. Second example, let us take here allyl and benzyl radicals. Allyl and benzyl radicals. Yeah, in this, let us see here how the stabilized. Here in this, what is the resonance? Resonance will be involved here. Second factor we can see here. Yeah, you see that CH2 double bond CH2. It is a free radical. You know that very well. It's a resonance how it looks. Again CH2. This bond is shifted towards this, and CH double bond, only half arrow you have to show here. CH2 only half arrow. Yeah, this is the resonance. And in case of benzyl also same manner, you can observe here. Single bond, you can see, double bond is there. Here only single bond. Now what happens? It's a free radical, benzyl free radical, we call it as. Now what happens here? Shifting of this bond takes place in this manner. It is remain same. It is also remain same. Double bond CH2, it's a single one. Again, half arrow you can see here. Single bond, formation of double bond takes place, CH2, you can see that. Yes, you can further. Idi. Yeah, you can observe like this. Here double bond is formed, again free radical, double bond CH2. It will be continued in this manner, we can say here. Finally, again it comes to, by the changing of position, final structure you can say here. Again, shifted towards this. Yeah, you can see. CH2. Finally it comes. In this manner, the resonance takes place in free radicals, we can say here. Yes, actually other than this we can see here the steric factor, one more factor we can say here, steric hindrance, we can say bulk. If it is bulk, like tertiary free radicals, when you take here, the stability depends on formation of tertiary butyl free radical by removal of hydrogen atom from isobutane is favored. Okay, you can see that when you observe isobutane, you take here for example. See, this is also a factor which can influence the formation of free radical or stability of free radical. Stability of free radical, you can say here, depends on also steric factor also. Yes, how the steric factor it influences, let us see example. When you take isobutane, the formula of isobutane is CH3 CCH3 CH3 H. This is called isobutane. Now what happens? Free radical can be obtained. How it is obtained? Already we know that by the thermal or photochemical. Two factors we have seen here. Right, thermal or photochemical, H nu, you say that. Then what happens? This bond is shifted towards this and one bond is shifted towards that. When you observe CH3 C CH3 CH3 free radical, and H will be removed. Okay, when you observe methyl groups, there is a steric repulsion. Steric repulsion means there is a repulsion between these two methyl groups, and these two methyl groups. Actually it is see the bond angles here, how much, the bond angles here and here, here and here, here and here, in between these, in between all of these, the bond angle is 109 degrees, 109.5 degrees actually. Now when the free radical is formed, it becomes 120 degrees. I have shown, we have to show like this, that free radical exact structure, it can be like this. You see, in all these it is a free radical. The bond angle is how much, here in all these cases bond angle is 120 degrees. You can say this is a free radical, you can say that. Empty orbital will be there, that empty p orbital will be there, that empty odd electron is present in empty p orbital, keep that in mind. Okay, here it is, means the steric repulsion will be removed. Okay, the steric repulsion, there is a steric repulsion arises, okay, due to that bulky nature. Okay, that's why tertiary free radical, this is called which free radical? Tertiary free radical can be obtained easily, okay, by the factor. That's why free radical can be obtained easily, we can say here. Okay, yeah, this is the about free radicals. And the next one we can say here carbons. The next one, let us see here about carbons. Carbons we can see here. Right, how can we show the carbons? Let us see here. Okay, you see carbons can be defined as a neutral divalent carbon intermediates. Okay, yeah, neutral divalent carbon intermediates. These are neutral divalent carbon intermediates. Okay, in which what happens? Carbon is covalently bonded to two atoms, in which carbon is covalently bonded to two atoms. Two atoms and two non-bonding orbitals. Two non-bonding orbitals, it is important. Two atoms and two non-bonding orbitals, because those are not participated in bonding. Carbon should have 4 valency, but only 2 atoms are attached, 2 valency completed, and remaining 2 are non-bonding orbitals will be there. Okay, yes. Yeah, containing 2 electrons between them. Okay, containing 2 electrons between them. I'll show you. Because these 2 electrons, actually, you know, carbon has 4 unpaired electrons, 4 valence electrons in first excited state, and 2 atoms are bonded and 2 bond pairs are formed, we can say here. And remaining 2 unpaired electrons, total 4 unpaired, among 4 unpaired electrons, 2 unpaired electrons form 2 bonds, and remaining 2 unpaired electrons are remains same between them. That's why containing 2 electrons between them, this is carbene. Okay, here there are 2 possible kinds of carbons theoretically. Okay, theoretically how many? Two types of carbenes are there. Two types of carbenes. Theoretically. Important, keep that in mind. 2 types of carbene theoretically, you can say here singlet carbene, triplet carbene. See, first one is what? Singlet. Singlet carbene, and the second type is triplet carbene. Okay, singlet carbene and triplet carbene. Two types of carbenes are there. Keep that in mind. Yeah. Actually, here, see, in singlet carbon, three hybridized orbitals are utilized in the forming of two covalent bonds, whereas third hybrid orbital contains the unshared pair of electrons. Okay, you can see here in singlet carbene, yes, in case of first case, let us see here. It's important, you have to keep that in mind. In singlet carbon, what happens here? Totally three hybrid orbitals are there. Among those, okay, two orbitals are utilized for the formation of covalent bond. Okay, total how many hybrid orbitals are there? Three hybridized orbitals are there. Okay, yes, you see, and two hybridized orbitals form two covalent bonds. How many covalent bonds? Two covalent bonds. This is first one. And the second type, you say case second one B, you see that. In this, what happens here? One, see, the third hybrid orbital contains the unshared pair of electron. Third hybrid orbital contains the unshared pair of electrons. Unshared pair of electrons. That pair of electrons are present. Okay, that means how many? It is incomplete octet. Keep that in mind. Two covalent bonds means how many electrons? 4 electrons, because each bond contains 2 electrons. That's why 2 into 2 covalent bonds means 4. And one unshared pair of electrons means how many electrons? Total 2 electrons. That means how many completely? 6. Only 6 electrons. It is, that's why it is carbene is highly reactive species. Keep that in mind. It does not completed octet. Keep that in mind. Okay, either singlet or triplet. Keep that in mind. You see that. Okay, yeah, next one you can see here, the second type, triplet carbene. When you observe, let us talk more about singlet carbon, no problem, because you can see here, when you observe, the unhybrid orbital remains vacant because fourth orbital also is there. Total how many orbitals we said? 4. 4 orbitals, 4 contains 4 unpaired electrons, we can say here, but here only 3 are hybridized and one hybridized p orbital remains vacant. Yes, keep that in mind. The unhybridized orbital p orbital remains vacant. Yes, that's why here, therefore, what we can conclude from this, singlet carbene resembles carbocation very closely. It's important point. Singlet carbene resembles resembles a carbocation. Very closely. Okay, you can say here. Okay, yes. But when you observe here, triplet carbene, it is sp hybridized. Okay, triplet carbene is what? Sp hybridized, whereas singlet carbene is sp2 hybridized. Singlet carbene is sp2 hybridized, and triplet carbene. Second type, what we said? Second one is triplet carbene. Triplet carbene is sp hybridized. Sp hybridized, and it is a linear or non-linear. It may be a linear or non-linear species. Point B is what here? It is a linear or non-linear. Species. We can see here. Yes, here these two hybrid orbitals. Okay, hybrid orbitals involved in the bond formation with two groups. Okay, in two hybrid orbitals, because sp contains how many? Two hybrid orbitals are involved in the bond formation. Are involved in the bond formation with two groups. With two groups. Okay, and the two electrons, okay, the two electrons are placed on each two electrons are placed on each one, you can say here, one each in equivalent, in the equivalent mutually perpendicular. Mutually perpendicular orbitals. You can say here. Right. Yes, here we can say here electrons have parallel spins. Carbons with these said to be in triplet state. Okay, you can say here. Right, one is paired up, another one is placed, two electrons are placed one each, because you see, that's why you can say that Triplet contains electrons have parallel spins in triplet. D, point D is what here? Electrons have parallel spins. Which electrons? Two electrons. Two electrons have parallel spins. You can say here. Okay. Yes. Right. This is about let us stop here. Shall we can continue this in next video? Okay. Yeah. How the carbon will be generated? Let us see here, and some more intermediates. We can see that in next video. Video length becomes more. Okay. Thank you. Thank you very much.